All right, so we've got some really interesting research to dive into today. It's a pretty radical idea, suggesting that, well, everything in the universe is basically about motion.
Hmm. Yeah, it really kind of rewrites the script, doesn't it? No forces, particles get a whole new look. Even time.
You know, instead of thinking about the universe as all these separate objects pushing and pulling on each other, it's more like this grand interconnected dance of motion.
Yeah, that's the core of it, really. It's suggesting motion, the fundamental force, not just a side effect.
Okay, yeah. I'm already feeling my brain doing backflips. So where do we even start with this? Let's go back to the beginning, like the beginning. These papers talk about a motion cascade event, or MCE, instead of the Big Bang, right? So what exactly is that?
Well, the MCE, it kind of throws the whole exploding universe idea out the window.
Hmm.
Instead, it suggests that before everything we know, there was this state of perfect equilibrium, like total stillness, a delicate balance of energy, but no motion whatsoever.
So not a sudden burst from nothing, but more like a transition. But what would even cause that kind of perfect stillness to break down?
That's where it gets tricky. You see, the papers describe this perfect equilibrium as inherently unstable. Think of it like a house of cards. The slightest disturbance can cause the whole thing to collapse.
So what was the cosmic nudge then? What set off the whole motion cascade event?
That's the million-dollar question. The research doesn't really give us a specific cause, but it suggests that even in total stillness, there's still potential energy. And any little fluctuation, even a tiny variation in energy density, could have been enough to disrupt that balance.
Okay, we've got a perfectly still universe with this tiny energy imbalance. How does that become galaxies, stars, planets, everything we see today?
Well, they propose this imbalance triggered a cascade, a chain reaction of motion. Energy's always trying to redistribute itself, find a new equilibrium, right? But instead of just scattering randomly, this energy began to form organized structures.
So how does chaotic energy become ordered, like the universe we know?
That's where the idea of spin comes in. The research argues that rotational motion, spinning, is the most efficient, the most self-sustaining type of motion, like a spinning top. Once it gets going, it takes very little to keep it spinning.
So instead of dissipating, the energy starts swirling, creating these little spinning pockets of energy.
Exactly. And those spinning loops pulled in more and more of the surrounding energy, becoming larger, more complex. They call it the great spin-up, like the universe decided to take a spin class, right?
Huh, I like that. But how do we get from spinning energy to actual, particles, the stuff that makes up everything?
Well, they propose that as these spinning energy loops hit certain thresholds, critical points of motion, the first particles start to emerge, specifically quarks, which, we usually think of as the fundamental building blocks of matter.
So instead of being fundamental, quarks are just incredibly concentrated bundles of motion.
That's the shift in thinking this theory is going for, yeah. And it's not just quarks either. They suggest that all particles, even electrons, are just different expressions of this structured motion. Like there's a whole motion spectrum.
Hold on, a motion spectrum. What does that even mean?
Well, think about the electromagnetic spectrum. Different light frequencies create different colors. The motion spectrum is kind of similar. It suggests that particles are defined by how their motion is structured. Their spin, vibrations, how they interact with the motion fields around them.
So not a universe made of static particles, but a universe where everything's constantly buzzing, vibrating, spinning, a cosmic dance. I'm starting to see why this is such a huge change from what we thought we knew about physics.
It really challenges the foundation, yeah. And if motion is the foundation, well, that changes how we understand everything, from gravity to, well, maybe even consciousness.
Okay, I'm definitely ready to go deeper down this rabbit hole. Let's start with gravity. These papers claim it's not a force at all. How does that even work?
Instead of a force pulling things together, they're saying what we perceive as gravity is really just an emergent property of these motion fields interacting. Imagine, for example, a planet orbiting a star.
All right, picture it. Earth around the sun.
Now, instead of the sun's gravity pulling on the Earth is actually following the natural contours of the sun's motion field, kind of like a marble rolling around a bowl.
So it's not being pulled in, but more like guided along a path by the sun's motion.
Yeah, exactly. And of course, the Earth's own motion field is influencing the sun too, and so on. It's this complex interplay of motion that keeps everything in balance.
Okay, but why would things fall towards larger objects in the first place? If it's not a pull, what's guiding it?
Well, remember, space isn't actually empty. It's full of these interacting motion fields. And the motion fields of larger, more energy-dense objects, they create a kind of a motion gradient that influences the motion of smaller objects nearby.
So it's like a cosmic current.
Yeah.
Something that smaller objects are swept up in.
That's a good way to think about it. Instead of gravity as a force, it's more like a natural consequence of how objects with different motion levels interact and influence each other's paths.
But what about mass? If gravity isn't a force, why do objects with more mass have a stronger gravitational pull?
They suggest that mass is actually a measure of how much an object resists changes to its motion state. Objects with more mass have more complex, more structured motion fields. They're made up of more particles, all swirling, vibrating.
So a bowling ball has a more complex motion field than a tennis ball because it has more particles contributing to that overall motion.
Right, and that complexity creates a steeper motion gradient, which affects the objects around it more strongly.
Okay, so the more mass of the object, the more pronounced its motion field, and the steeper the slope that other objects are guided along.
Precisely. And this framework, you can apply it to understand everything from planetary orbits to how galaxies form.
This is incredible. It's like we're taking this invisible force we call gravity and turning it into something we can almost visualize, this swirling, interconnected web of motion.
And this is really just the beginning. This framework, this idea of motion being fundamental, it has the potential to explain all of it. The fundamental forces, the particles, how they combine to create everything we see.
All right, this is blowing my mind. Where do we go from here?
So are you ready to see how motion shapes, how molecules are made?
Yeah, absolutely. We've redefined gravity. So now I'm really curious to see how this motion framework changes how we think about chemistry.
All right, so imagine atoms, not as these static things with electrons just orbiting around them. Think of them more as centers of these swirling motion fields. And it's how these motion fields interact that create what we think of as chemical bonds.
So it's less like atoms snapping together, more like a synchronized dance?
Yeah, exactly. The papers talk about electron shells, but not as fixed orbits. They describe them as zones of stability within the atom's overall motion field. And when atoms bond, they're not just exchanging electrons. They're syncing up their motion patterns, trying to reach this more stable, lower energy state.
So covalent bonds are more like a perfectly coordinated waltz between atoms.
Yeah.
That's way more elegant than how I learned it back in school.
Yeah, a little more exciting than those old diagrams.
So what are ionic bonds then? Where one atom supposedly donates an electron to another.
Well, in this framework, ionic bonds are more about correcting motion imbalances. One atom has this stronger motion field, and it can influence, kind of stabilize the motion field of another atom, and that leads to what we call an ionic bond.
So it's less about giving and taking, more about finding a balance between their motions.
Precisely. And this idea of motion compatibility, that explains why certain atoms only bond with certain others, right? It's not random. They're inherent motion patterns. They have to synchronize well to make that bond stable.
So the periodic table, it's not just a list of ingredients, but more like a cosmic dance card showing which atoms are going to find a rhythm together.
I like that. A very poetic way to put it. And this motion-based idea, it goes beyond explaining just individual bonds. It explains why molecules, these complex arrangements, form in the first place.
Okay. Yeah, I'm listening.
So certain configurations of atoms, when they link up, they create a more stable, lower energy motion state for the whole system. It's like, think of a group of dancers. They find a formation that takes less effort to hold,
So molecules form from this drive towards motion efficiency, trying to be more stable.
That's the core idea. And the shape of a molecule, whether it's linear or tetrahedral or something way more complex, it all comes from these motion fields, right? They're pushing and pulling, trying to find that most stable, harmonious configuration.
Wow, so it's not just atoms bonding. It's this whole choreography of motion happening at the molecular level. It's really changing the way I picture, that microscopic world. But what about chemical reactions then? How does this idea of motion change how we understand, like how molecules transform?
Okay, so instead of picturing reactions as breaking and forming bonds, think of them as shifts in how synchronized those motion fields are.
So not like snapping Legos apart and rebuilding, more like the molecules are switching partners, changing their dance routines.
Yeah, that's a great way to visualize it.
So what determines then, like whether a reaction happens spontaneously or needs a push to get going?
That's a great question. So the energy that's released or absorbed in a reaction, whether it's exothermic or endothermic, that reflects how much the overall motion stability changes during the reaction.
So reactions that become more stable, they release energy. And reactions that need more energetic motion, they need energy input. Makes sense. What about catalysts then? Where do they fit in all this?
Catalysts, they're like the expert choreographers. They help molecules transition between these dance moves more smoothly by creating these temporary motion states that lower the energy barrier for those transitions.
This is brilliant. It takes all these abstract ideas from chemistry and makes them like visual and intuitive. I can really see how this motion framework connects physics and chemistry so beautifully. But what about biology? Can this idea of everything being motion, can it really explain how complex life is?
Well, that's where things get really fascinating. Imagine a cell, not as a static collection of molecules, but as this dynamic, self-organizing system of motion. It's buzzing with activity, you know.
But not a microscopic factory, but more like a bustling city. Everything's moving, coordinated.
I love that analogy. And things like metabolism, they're not about consuming energy in the traditional sense. They're about redirecting and restructuring energy's motion states. It's what keeps the cellular city alive and dynamic.
Like a city's power grid.
Yeah.
Always adjusting the energy flow, keeping things running smoothly.
Exactly. Even molecules like ATP, which we usually think of as just energy carriers, they become these intermediaries, helping to shift and stabilize motion states within this cellular city.
And enzymes, those proteins that help reactions happen, they're like the city's traffic controllers then, making sure everything flows efficiently.
Exactly. They align molecules into more efficient synchronization states, so those critical reactions happen faster, like choreographing the molecular traffic to optimize the city. But what about the blueprints for this city, right? Where does DNA fit into all this?
Yeah, that's what I was wondering. Does DNA still hold the instructions for building and running the cell in this, motion-based world?
This is where things get really mind-blowing. Instead of thinking of DNA as just storing information, think of it as encoding motion patterns for molecular assembly.
So DNA is less like a blueprint, more like a choreographic score, dictating all movements of the molecules that build and maintain the cell.
That's a fantastic way to picture it. And mutations, changes in the DNA sequence, they become alterations to that intricate choreography, leading to different molecular outcomes.
That's such a dynamic way to think about genetics.
Yeah.
It's amazing how this motion framework changes our understanding of biology at every level, from simple molecules to these complex cellular processes. But can we go even further with this? Can this idea of everything being motion, can it explain even more complex stuff?
That's what we'll get into next. This final paper, it explores what this framework means for the brain, for consciousness, even for the universe as a whole.
Okay, I am ready to have my mind blown wide open. Let's do it. All right, so we've come a long way. Starting with the universe's origin as this cascade of motion, then motion shaping atoms and molecules, even that intricate dance of life itself. And now this final paper takes us to the biggest stage imaginable, the universe as a whole. I'm ready to see the cosmos through this motion-based lens. What have you got for me?
Well, this paper, it brings up this fascinating idea. They call it universal scaling of motion. It suggests that those same principles of motion that govern the microscopic world, they apply to the largest structures in the universe too. So the elegant choreography we see at the atomic level, it's mirrored on a cosmic scale.
So the same moves that quarks are doing inside an atom, galaxies are doing that across vast distances.
Yeah, that's the essence of it. So instead of thinking about planets and stars as isolated objects held together by gravity, think of them as these massive swirling motion fields, all embedded within this even grander web of cosmic motion.
So it's not a collection of separate things, but more like one interconnected symphony of motion, from the tiniest particles to those huge galactic superclusters.
Precisely. And this whole idea of motion scaling, it might actually be the key to understanding some of the biggest mysteries in cosmology.
Okay, like what? We've already redefined gravity. What other puzzles could this framework help solve?
Well, take dark matter, for example. That invisible stuff we can't directly observe, but we know it's got to be there based on its gravitational effects.
Yeah, right? Dark matter. It's one of those big enigmas in astrophysics.
This paper suggests that instead of being some exotic, undiscovered particle, maybe dark matter represents motion influences. Influences that our current models of the universe just aren't accounting for. It's not some new substance. It's a consequence of the universe's complex motion structure.
So instead of looking for a mystery particle, we need to rethink how motion shapes the cosmos on a grand scale.
That's the intriguing possibility this framework offers. It also gives us a new perspective on dark energy, that force that's driving the accelerated expansion of the universe.
So instead of a separate force pushing everything apart, could dark energy just be another aspect of this universal interconnected motion?
Exactly. Imagine the universe not as expanding into space, but as constantly reorganizing its internal motion structure. This continuous restructuring, it creates the appearance of expansion from our limited perspective.
So it's not expanding outward, but re-choreographing itself from within. A cosmic dance floor that's constantly in motion. It's a mind-boggling concept. But if we accept this, what does it mean for, well, for how we understand space and time?
That's where things get really profound. Remember we talked about time as an illusion created by our brains tracking motion patterns.
Yeah, the idea that time is more like a verb than a noun, a consequence of motion.
This paper takes that even further. It suggests that space itself might be an illusion too, or at least not what we traditionally think of it as. It's not an empty backdrop, but an emergent property of the universe's dynamic motion structure.
So the universe doesn't exist in space. Space is created by the universe's motion.
That's the proposition. Think of it like the swirling patterns in a Van Gogh painting. They're not separate from the canvas. They're part of its structure. Space might not be a container, but the fabric woven by this intricate dance of motion.
This is paradigm-shifting stuff. If the universe really is this vast, interconnected system of motion, what does that tell us about our place in it? Are we just passive observers, or do we actually play a role?
Well, this framework suggests we're not just watching the cosmic ballet, we're dancers in it. Our thoughts, our actions, they all contribute to the universe's motion structure.
So we're not just along for the ride, we're shaping the choreography as we move through the universe.
Exactly. Just like one dancer's movements can influence the whole routine. Our choices, they create ripples through this interconnected web of motion.
It's kind of humbling. And empowering, too, to think we have a part in this grand cosmic dance. It suggests this level of interconnectedness, responsibility that we don't often consider.
Absolutely. It's not just changing how we understand the universe. It's inviting us to rethink our role and the impact we have on the cosmic dance as a whole.
So as we wrap up this deep dive into the universe's motion, what's the one thing you want listeners to take away from all this?
If I had to pick one thing, it's this. The universe is way more interconnected and dynamic than we tend to think. It's not just a bunch of stuff sitting around. It's this breathtaking symphony of motion. And we're not separate from that. We're notes in it, our movements shaping the music of the cosmos.
That's a beautiful thought to carry with us. So everyone listening, the next time you look up at the stars, remember, you're not just looking at points of light. You're seeing a cosmic dance that's been going on for billions of years. A dance you're a part of.
And maybe by understanding the universe this way as motion, we can learn to move in ways that create an even more beautiful cosmos for us and for generations to come.
It's definitely a future worth striving for. Thanks for taking us on this journey. It's been amazing exploring the universe through this lens of motion.